Okay, so let's do this thing. Suppose that you have a subsequence. Okay, everybody take 1 minute and take a look. Okay. Suppose you have a subsequence. Click that in conversion dot. Suppose it comes down. Exists something.
That was supposed to be an MJ.
Okay, that's okay. That's okay, sorry. Okay, yeah, okay.
Could there be one more step between, since every element of x of n is either in x of n sub j or x of n sub k, then n greater than n implies x of n minus L is less than epsilon. Could there be like another step between there, or is that like a direct result?
What would be your next? What would be your next? What would you add in?
I don't know. I mean, it makes sense, but then maybe something that would make it more clear.
Yeah. So what I would say about this, and it's not wrong. It's not wrong, but it's sort of skipping over a small step, which is that you have this subsequence. You have this other subsequence. And it's actually not that there exists an n1 such that nk bigger than n1 implies this, but that there exists a k such that if k is bigger than k, then n sub k. Right? It's actually, you're looking at this thing, but technically at least it should be this thing that you're looking at. Do you guys see what I mean?
Yeah.
Right? That right. So you've got your sequence A1, A2, A3, A4, A5, blah, 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 right? You've got your this is AN1, say AN2, right? There's an AN3 somewhere, AN4, blah, blah. The other guys are the AM1, AM2, AM3, AM4, AM5. Okay, right, so these guys. Right, like that. And so you're. So I mean, it's not wrong, but you sort of you sort of slid it together a little bit. You know, it might be clearer. I think it would probably be clearer to write it like this. Right, there exists a capital K such that if you're past that in the n sub k sequence, then you're less than epsilon. There exists a capital M such that if you're past that in the M sequence, then you're bigger than that, right?
J.
Oh, J. There exists a
Big
capital
J.
J such that little j is bigger than big J, like that, right? And then,
Just change the max.
yeah, then the max would be not kj, but in fact it would be, yeah, n capital K and m capital J, right? Right? As long as you're bigger than that, right? then if and bigger than that implies that A sub n is either n sub k with k bigger than k, or m sub j with j bigger than j. Right?
Can you explain that step?
Okay, so let n be the max here. Okay, then if if little n exceeds that, since A sub n is either in the A and k or the A mj sequence, it must be either A and k or A and j.
So we're talking about a specific element.
Yeah. So choose any n bigger than this max guy. Okay. We know it's got to be in one of these sequences. Okay. So it's got to be, you know, something like this or something like this, right? For some k naught or for some j naught. Right? Right? But that k naught would be bigger than k, right? Because we're past n sub k, right? And the j naught would be bigger than j, because n is bigger than mj, right? And so in either case, oh, I'm sorry, I'm writing A instead of X, but just go with it. A n minus L is less than epsilon. But I mean, what you wrote was not wrong, but it just requires just a tiny bit of extra mental effort. And then, if, like this, then it doesn't require that extra mental effort. You know, basically, proofs should be written so that the reader can read them, you know, without thinking. In some sense. Although I should say, in reality, that's not the case. Like if you look at a paper, they'll be like, this happens and then this happens, and then you spend about a couple of days trying to figure out how that worked, or never figure it out. Okay. Okay. So okay. So I'm gonna actually. I was gonna finish the proof of completeness, but I think let's start off with the continuity section, and if there's time, then we'll do the proof of completeness. Because you remember the way that you did it in class was by contradiction. I said I was going to do a direct proof. Just doesn't matter that much, but let's get on to the next thing. Okay. Section 17, continuity. So, well, it's not. Section 17, continuity. Okay. So here is the book's definition. say you have f on some domain. So this is some domain, and this domain is contained in R, right? And you have some point x naught in your domain. Okay. So there's two parts to this. If given any sequence x of n contained in your domain, such that the limit of x of n is x naught as n goes to infinity. If given any sequence blah, we have that the limit of f of x of n as n goes to infinity equals f of x naught, then we say f is continuous at x naught. It would probably make more sense to call this x naught x infinity, right? Because the xn's are going to it, right? As n goes to infinity, you go to x infinity. But I think people don't like to use, people generally use x naught for a fixed point. So that's why we're using that. Okay, part two. So you have some subset S, a subset of D. If F is continuous at X for all X in that subset, then we say F is continuous on that subset. So the first definition is continuity at a point, continuity at a point. And the second definition is continuity on a set. And of course, being continuous on a set just means you're continuous at every point in that set. Okay. So just some simple examples, right? Right. Suppose you have the function f of x is constantly equal to 1, right? And you have some x naught, right? And you say, is this continuous? What does this mean for this to be continuous? Is f continuous at x naught? It should be. Right? It's a continuous function. By the book's definition, what do we need to see? We take any sequence, right? So take any sequence x of n such that x of n goes to x naught. Does f of xn converge to f of x naught? Sure, right? Because all the f of xn's are 1, right? They're all equal to 1. And these guys are equal to 1. So we're asking, right, does the limit of f of xn equals f of x naught? Like, in other words, 1? As n goes to infinity? Well, f of xn is 1, right? So we're just asking, does the limit of 1 equal 1? Sure. So yeah, we're continuous at every point. Okay. So this is how you would use the book's definition to check continuity. Right? Or, suppose you have something like this. Another example. F of x is x if x is rational, and negative x if x is irrational. It's x if x is rational, it's negative x if x is irrational. So on all rational points, it looks like f of x equals x. On all irrational points, it looks like f of x is negative x. Where is this function continuous? By your reasoning? If you looked at this function and said, where is this function continuous?
Wait, at 0?
At 0. Yeah, this function is continuous at 0. Secretly, you know f is continuous at 0. So what do we have to ask? We have to ask, is the limit of f, so our claim is that f is continuous at 0. Actually, let me do it easier one before we do that one. So f of x is x squared. And let's show that f is continuous at 0. Let's show that f is continuous at 0. Let's do that first. Okay. So we need to show that if x of n converges to 0, then the limit of f of x of n is f of 0, right? Which is, of course, 0 squared. Okay. Well, is that true? Is that true? Yes, right? Because what's f of xn? Well, f of xn is limit of xn squared, right? Right? The limit of f of xn squared, right? And so why is that equal to 0?
Because as n goes to infinity, xn goes to 0.
Yeah, right? Since xn converges to 0, right, the limit of xn squared is going to be the product of the limits by your limits and arithmetic theorem, right? By limits and arithmetic, this is going to be the limit of xn times the limit of xn, right? And that's 0. Okay, so this is how we see that this function is continuous here, and we could have done this at any. We didn't have to do this at 0. We could have done this at c, right? Right. This would be c squared, and then we would just say since xn goes to c, this is going to be c times c, in other words, c squared, right? Right. Okay. So in fact, this function is continuous on the entire real line. Because it's continuous at every point on the real line. Okay. Now, how about this guy? We want to show that. So suppose xn goes to 0. How do we show that the limit of f of xn equals f at 0? F at 0 is just 0, right? Because 0 is a rational number. I mean, even if it weren't, we'd still get negative 0, which is 0. How do we show that the limit of f of xn is that? Well,
we can make subsequences. And the limit of the subsequences.
Yeah, in fact, we could use the theorem that the problem we just did, right? You could say, take any sequence. This is great, Mark. Take any sequence x of n such that x of n goes to 0, right? Then x of n, let x of n k be the rational elements. Let x of mj be the irrational. Right? Both converge. Both converge to 0. Right?
Professor,
Yep.
when we say, under the thing, say x of n goes to 0,
Mhm.
is that like something we're given, or where did that come from?
So that is a proof. We want to show that f is continuous at 0. What do we have to do? We have to show that we want to show that if x of n goes to 0, then this goes to 0. So, okay, so now that I'm putting it all together, I don't need to say this because I've already written it. Right? Let this guy be the rational ones, let these guys be the irrational ones, right? Then the sequence fxk, right? So fxk can be broken up into f, x, and k, and f, x, mj. Maybe partitioned is a better, more mathematical sounding word. It can be partitioned into these two sequences. Anyway, we know what we mean here. And we see that, well, the limit of these guys is the limit of these guys were the rational guys, so we just get the limit of x and k. Right? The rational guys, f on a rational number is just that rational number. Right? F on an irrational number is negative that irrational number. But that's 0, and that's, 0 also. By the homework problem, we see that fxn also goes to 0. Which is not at all how I was going to prove it, but that's great. If you didn't think of the homework problem, which is kind of a funny way to do it, you could prove it directly, right? You could use some epsilon n argument. That's one way to do it. Or, better, you could use the squeeze theorem. You can use the squeeze theorem, so alternative proof. Like you'd say, well, look, let xn go 0, then f of xn is either xn or negative xn. So f of xn in absolute value is smaller than xn. Smaller than the absolute value of xn. Or maybe, I mean, let me make it more squeeze theorem-like. So f of xn is trapped between the absolute value of xn and negative the absolute value of xn. Right? Because it's actually either one or the other. Now, the limit of the left side is 0, and the limit of the right side is 0. So by the squeeze theorem, the limit of the middle guy must be 0. Oh yeah.
On this one?
Yeah.
The previous one, where
Yeah.
we say both converge to 0, is that using the claim that we've shown that if you have subsequences, they converge to the same limit?
Yeah, right, because they are subsequences of a sequence that converges to 0. So, yeah, so I think if I wanted to be proper, I would say by previous theorem, or by the theorem that says subsequences of a convergent sequence converge to the same limit. Okay. Okay. So you're seeing how to use the book's definition to prove continuity, and that's one way to do it. Let me show you the more standard definition of continuity. Okay. So yeah, that definition is the book that the definition that the book gave. For us, it's going to be equivalent to this definition. Okay, but the thing is that it's not always equivalent to this definition, depending on your space. This is sort of the more usual definition, but we'll also have another definition of continuity. There are multiple definitions of continuity, and you can sort of gauge an undergraduate's level in her training by saying, what does continuity mean? Right? If they say, oh, if you take this and this, you get an open set, you're like, oh, okay, then I know what kind of courses you had. Right? You can tell what they've taken by how they respond to this question. There's a topological definition of continuity. There's this definition, there's other definitions. Or if they just say, well, you can trace it without lifting your pencil, then you know they haven't had any math yet. Okay, so here's the standard definition, I would say. So again, you have some function on a domain, and you have some point in the domain. So okay, I'm going to give two definitions. Okay, so they're basically the same definition. If for every epsilon greater than 0, there exists a delta greater than 0, such that the distance between f of x and f of x naught is less than. Thanks. I'm going to say it again. Wait a minute. Okay. There exists a delta such that f of x, the distance between f of x and f of x naught is smaller than epsilon whenever x minus x naught is less than delta, then we say f is continuous at x naught. Okay, so the picture is like this. We have, actually let's use that last picture. We have a function. We say it's continuous at x naught if whenever somebody gives us an epsilon, so our x naught is here. If whenever somebody gives us an epsilon, you can find a delta so that everybody within delta of x naught has an output that's within epsilon of f of x naught. Yes.
I'm a little bit confused how come we don't relate delta and epsilon, because you can kind of think about it as like f of delta equals epsilon. You know, like it's not inherently necessary, but there's that relationship to it, right?
Yeah, but that might not happen, so that's why we don't. You don't. I mean, you can sort of think of it that way, but that won't necessarily happen.
Okay.
Okay, so that's why we leave it off. And certainly there's a relationship, right? There's a relationship. You know, this is sort of like saying you can play the epsilon-delta game. Okay, given any epsilon, you can find a delta that works. Okay, this delta, right? So this delta depends on your epsilon. Right? The delta is dependent on your epsilon. If whenever you're given an epsilon, there's a delta that makes things work, we say the function is continuous. Okay, so right, so I have some function, right? I have some function. I have some x naught. I have some f of x naught. Okay. And what we're saying is that given any epsilon, you can find a delta so that the guys who are close within delta of x naught, so that everybody, you can find a delta so that everybody in here, so this is delta plus epsilon, delta, I'm sorry, x naught minus delta, x naught plus delta. Everybody inside here is all the outputs there are in this epsilon neighborhood of f of x naught. Okay. And if somebody says, you know, and you can do that for any epsilon. So if I say, I'd like you to stay this close to f of x naught, well, you can find a place where that happens. Okay. If I say, I want you to stay within a billionth of f of x naught, I can say, I can find a place where that happens. And if you can do that for whatever tolerance I say, then that means your function is continuous there. Okay, so that's the definition of continuity at a point. That's the real definition, or the usual definition of continuity at a point. Okay, let me rephrase it. And this is not at all a serious change. Okay. If given any epsilon neighborhood of f of x naught, there exists a delta neighborhood and delta of x naught such that f of every point in the delta neighborhood lies in the epsilon neighborhood, then we say f is continuous at epsilon. Oh yeah.
How can you take the function of?
So this is a notation. I was just about, let me explain it.
Yeah.
So what this says is that if we say f of a set is contained in another set, what we mean is that f of A is contained in B for all A and A. Okay, we'll use this square bracket to indicate f of a set. This is just a notation.
Are those the same type of brackets?
No. I mean, these are parentheses, these are brackets.
What about for f of A?
This is a bracket.
Okay, it's the same thing as
This one over here.
bracket.
Yeah.
It doesn't have the bottom part.
Okay, please forgive me. Just understand that sometimes I'll write it and it may not have that. It may not have the bottom part. There you go. I mean, you're not completely off base in the sense that there are actually things that look like, there are actually symbols that look like this, right? The greatest integer lower than your number, etc. Like the smallest integer greater than your number. Okay, that's true. But we're not dealing with them here, so I am free to be a little bit sloppy. Okay. So what this is basically seeing this not on a graph. So this definition is basically like, let's not think of this as a graph, but let's think of this as a map. Right? Let's think of this as a map. You've got your x naught here, you've got your f of x naught here. Right? And right? You've got your x naught somewhere, you've got your f of x naught somewhere. And it's saying that whenever you have, no matter what epsilon neighborhood you're given, right? So here's your epsilon neighborhood of f of x naught. There's some delta neighborhood, right? Some delta neighborhood over here, that such that everybody in here gets mapped inside that epsilon neighborhood, right? And that's the same thing, exactly the same thing we're saying here. It's just a slightly different viewpoint. Okay. One that is better when you have things that are graphs, right? If you are dealing with things that are, maybe you've got a function on something that's not Euclidean space, right? Going to something that's not Euclidean space, right? Then what does it mean? You don't have a graph anymore, right? I guess in this course we're dealing with real numbers, so we don't have to worry about that. But this is sort of like the more flexible viewpoint. Okay, but they're exactly the same. In this case, they're exactly the same. No, they are exactly the same. Excuse me. Okay. Let's stop here. I think I have some homework to return to you.